Okay, so in this video, what I want to do is I want to give you a couple more examples of constructing explicit and recursive functions from sequences. So let's say that I give you the following sequence. Let's say that we have the sequence 3, let's start with 3, 7, 11, 15, and we'll do ... to make this an infinite sequence. So this is an infinite, because we have the ... it means it continues on indefinitely, so it is an infinite sequence. Now your task or your goal for this problem is to construct the recursive and the explicit function for this sequence. So here's your sequence. I want you to construct the recursive and the explicit function for this sequence. So I'll do that in two different colors here. Let's do recursive. Let's do explicit over here in a different color, explicit. And I'm just going to go ahead and walk you through how I solve for the recursive and the explicit function that generates this sequence. Now, let me just go ahead and tell you, there is no step-by-step procedure for constructing recursive or explicit functions. There's just not. I'll walk you through how I think about it, but it's not the only way. It's not even necessarily the best way. It's just the way that I do it, and I'm going to show you how I do it. But if you have another way that works, and it just happens to be a little bit different than mine, then use that method. That's perfectly fine. And even if your end result is not the same as mine, as long as your functions generate this sequence, that's okay too. That's perfectly fine. So let's start with the recursive function, because if there were a step-by-step procedure, I feel like the recursive process is going to be as close as we can get. So let's just start by stating what we're looking for. We want to find a recursive function a of n. We want to find the recursive function a of n. And the first thing that we do when we're trying to find a recursive function is we have to directly state what the first term is. So I look at the sequence. Here's my sequence. I look at the very first term, and I have to define it. I have to state exactly what it is for my recursive function. So I state a of 1, that is my first term, is equal to 3. That has to be true. So I state that directly. I say a of 1 is equal to 3. Now let's see if we can figure out, or just write out, a of 2 and a of 3 and a of 4, and see if we can maybe identify a pattern that's showing up. So let's do a of 2 is equal to, so we know here a of 2, right? A of 2 was obtained by adding 4 to 3. So we added 4 to 3. So I could write this out. I could say this is the same. A of 2 is 3 plus 4. That's how we got it. So just to clarify, we know that there's a pattern here. So between every single term, right? If we start with this term, we add 4 to it to get 7. Then between the 7 and the 11, we're adding 4. We added 4. Now between the 11 and the 15, I'm adding 4. So that's the process. That's the sequence. And then to get the next one, I would add 4, and I would just continue that process all the way down the line. But wait a minute. Check this out. This 3, what else is equal to 3 here? Yeah, we said this a of 1 is also equal to 3. A of 1 is also equal to 3, so could I not just plug in a of 1 for 3? And some of you may say, well, what's the point of doing that? That doesn't seem like it's very helpful. And right now it doesn't seem like it's very helpful to you, but you'll see why in just a few moments, why we plug in a of 1. It's going to help us visualize or identify a pattern, and it's also going to help us construct our recursive function. Now let's do a of 3. So a of 3, that's going to be the third term, and we know that that was calculated by adding 4 to 7. So we find 7, add 4, that gives us 11. So 7 plus 4, that's going to be equal to 11. But look at this, okay? We also said that a of 2 is equal to 7. So if a of 2 is equal to 7, then we could plug a of 2 in for 7. So that would give a of 2, which is 7, plus 4. Now, hopefully at this point you're starting to see the pattern. Let's go ahead and write one more. Let's go ahead and evaluate a of 4 is equal to, so we know to get 15, let's erase that. We know to get 15, we take the previous term, which is 11, we add 4, and we get 15. So we do 11 plus 4, and that is the same as saying a of 3, because that was the previous term, plus 4. So at this point, you should be able to identify the pattern. And the pattern is, if we want to construct some general function a of n to generate this sequence, we would have a of some number n is equal to, now this is probably the trickiest part, is being able to identify what goes here. But if you notice that when we plug in 2, on the right-hand side of the equation is a 1. So this 1 is 1 less than the 2. Now when we plug in 3, look what's on the right-hand side, a 2. So it's 1 less than the 3. And then the same is true here. Here's a 4, and then 1 less than that is 3. So we're always going to have the function that is 1 less than the function that we are looking for, plus 4. So what does that look like in general? It looks like this, a n minus 1 plus 4. So just to clarify, this is the same, okay, as saying, well, it's not really the same, but this is our general function. Now let's test it. We can test it to make sure. So if I were to plug in, say, 2 for my n, I would get a of 2 is equal to a 2 minus 1, which is just 1, plus 4, which is the same thing that we got here. And you can actually go through and check and make sure that this general function works for every single term in our sequence. So really the last thing I need to make a note of, though, is that this is not exactly your final answer. You actually have to add with, at the end, with a of 1 is equal to 3. You have to state directly what your first term is, and then that is your final answer. So feel free to take a moment and check this, play around with this general form, because it may help you if you don't fully understand how I got this. Maybe it would help you to go in and plug in 2, plug in 3, plug in 4, and actually confirm that you get these numbers that I say that you should get here. So go ahead and take a minute and do that. Just test the function, play around with the function, and make sure that you understand that this will generate each of these terms. So if there ever was a step-by-step process for writing an explicit function, this is it. So for writing explicit functions from sequences, the first thing is I define my function. I say that there is some explicit function that we are looking for. In this case, I'll just call it b of n, but it doesn't really matter what you call it. You can call it anything you want to, and that's what we're looking for. Okay. Now there's some explicit function b of n that would give me, when I plug in 1 here, it would give me 3. When I plug in 2, it would give me 7. When I plug in 3, it would give me 11, and so on and so forth. Now, what I usually do when I'm writing explicit functions, if I know what the sequence is, I start by writing the first term of my function as the first term in my sequence. So what does that mean? So if I want to find the explicit function, I would start by writing b of n is equal to 3 plus something. So this is just a general way. Now, it's not always going to work, but for this particular sequence, it will. Now, ask yourself, if I wanted to get, say, this 7, what would I add to 3 to get this 7? Well, I would add 4. I would add 4 one time to get that 7. So let's maybe write this out so that way you can see the pattern develop, and then we'll come back up here to this part and we'll finish this general function. So let's see if we can see the pattern. So to get that 7, I'm doing 3 plus 4, and we're adding that 4 one time. Now let's look at the next one. So to get this 11, okay, to get this to 11, what should I add to 3 to get the 11? To get the 11, I would need to add 4 2 times to 3. So here, I would do 3 plus 4 2 times. So just to clarify, what I'm saying here is to get 11, to get this 11, and maybe it'll help if I just do this is equal to 7, so 7 is equal to that, 11 is equal to this, and to get this 11, I do 3 plus 4 2 times. So I need 2 times that, so 1, 2. Now if I want to get the 15, 15 is equal to 3, so 3 plus 4, 1, 2, 3 times. So plus 4, 3 times. Now notice what we have here. Every single time we would say that this is our A, well, we're using B here. That's B of 2, B of 2 to get the 7. This is B of 3, and this is B of 4. So you may notice that there is a pattern here that I can identify using by writing it out this way. So you can see that the 3's show up in every single term. So I'm just going to write my 3. It's always going to be 3 plus something. 3 plus something, 3 plus something. So I write down 3 plus something. Now look at this. This 4 shows up every single time. So it's always 3 plus 4 times something, 4 times something, 4 times something. So my general equation, I'm going to make a guess here, is it's going to be 4 times something. But the question is, what is this something going to be? Now you may notice, this 2 would be our n here. This 3 would be our n for the third term. Our 4 would be the n for the fourth term. And notice what we're multiplying the 4 by every single time. It's always 1 less than the n value that we're plugging in. So if this is 2, 2 minus 1, that's 1. If this is 3, 3 minus 1, that's 2. If this is 4, 4 minus 1, that's 3. So I make my guess that this function is going to be 3 plus 4 n minus 1. Now, this is my explicit function. So really fast, let me explain exactly why we call this this function explicit and why we call this function recursive. We called this function explicit because we could explicitly plug in any value for n and calculate any term along this sequence. So if I wanted to find the 23rd term, I'd plug in 23, 23, and just plug this into my calculator, and I could find the 23rd term. However, with the recursive function, it's not quite that easy. With the recursive function, I would actually have to know the term before. So if I want to find the 23rd term, I would have to know a of 23 minus 1. So a of 22, I would have to know the previous term before I could calculate the 23rd term. In order to calculate the 22nd term, I'd have to know the 21st. In order to calculate the 21st, I'd have to know the 20th. So I would have to start from the very first term and repeat this process continuously until I get up to the 23rd term. That is why we call this function recursive and why we call this function explicit. So if you have any questions after watching this video, just let me know. I hope this is sort of, you're starting to get used to seeing these types of functions. But go ahead and start your activity for the day, building the dominoes or matching the dominoes, and just let me know if you have any questions.